14.1 Elevators. An elevator always has two forces acting on it. The first force is the force of tension from the cables. Tension always pulls up. The second force is the force of gravity, which is always a downward force. The total force, F net on the elevator, is the combination of these two forces, force of tension plus force of gravity. F net, according to Newton's second law, can always be also calculated using mass times acceleration. And don't forget that force of gravity is also referred to as weight, which is mass times little g, which is negative 9.81 meters per second squared here on Earth. For example, an elevator has a weight of 8,500 newtons. What is the tension in the cables when the elevator is accelerating upward? At 2.5 meters per second squared. First of all, when you're given a force problem and you're given weight, it's pretty likely you're going to want the mass. To convert weight into mass, we remember that weight is down, so weight is 8,500 newtons down, or negative 8,500 newtons. And we remember that mass is equal to weight divided by little g. This is negative 8,500 newtons divided by negative 9.81, which gives us a mass of 866.4279 kilograms. Now that we have the mass, we can go about calculating the force of tension. The F net on the elevator is always tension plus force of gravity. We can rearrange this for tension. Force of tension is F net minus force of gravity. F net is mass times acceleration, and force of gravity is the weight. So force of tension is 866.46279 kilograms times the upward acceleration of 2.5. This is positive because it's up. Minus the weight, which is negative 8,500. Don't forget weight is negative, or your answer will be wrong. 1.1 times 10 to the 4 newtons is the force of tension in the cable. We can also look at the elevator from the perspective of inside the elevator. This is the perspective of the person who's riding the elevator. The person riding the elevator isn't aware of the cables or the tension. They're just in the elevator feeling the forces due to their acceleration. For the person inside the elevator, they have two forces acting on them: the downward force of their gravity and the upward normal force that balances it out. Force of gravity on a person is, of course, the person's weight. The normal force is the upward force of the floor pushing back on the person. We will also refer to this normal force as the apparent weight. This is because the normal force is how much the floor pushes up on you. Even though your true weight, the weight that you have in real life, is the force of the Earth's gravity pulling down on you, this is not actually what you feel to be your weight. What you feel to be your weight is your perceived weight or your apparent weight. Your perceived weight is the normal force. And in physics, we refer to this as your apparent weight. F net on a person standing in the elevator is always the combination of the two forces acting on them. Normal force plus force of gravity. F net is ma, Fn is apparent weight, or normal force, and Fg is your true weight, or your force of gravity. We'll use this formula to do our calculations in the next example. In this example, we're going to look at an elevator traveling from floor 1 in a building to floor 2. As the elevator travels upwards, at the start, it has an acceleration that is also upwards. Let's give this acceleration positive 4.2 meters per second squared. Because v and a are both up, we know the elevator is speeding up. At the top, the elevator is still traveling up, but it's slowing down to stop. So the acceleration is negative. Let's use negative 1.50 meters per second squared for our elevator. And it's slowing down because v and a are in opposite directions. Let's put a person in our elevator. They're about 50 kilograms. Now, the true weight of the person will never change no matter where the elevator is. This is mass times the acceleration due to gravity, which is 50 times negative 9.81, which is negative 490.5 newtons. This is the person's force of gravity. Now, as the elevator slows down to floor 2, the net force is normal force plus force of gravity. The normal force is F net minus force of gravity. Entering in some of our values, F net is mass times acceleration, which is 50 times negative 1.5 because it's slowing down, minus the true weight, which is negative 490.5. This gives us a normal force of 416 newtons. Notice that the apparent weight, as the elevator is going with a downward acceleration, is much less than the actual weight. So as the elevator has a downward acceleration, you perceive that your apparent weight is much less than your actual weight, and that's why you feel lighter and sometimes a little dizzy. As the elevator is speeding up at the bottom, it has an upward acceleration. F net is still normal force plus force of gravity, so normal force is F net minus force of gravity. This is mass times acceleration, which is positive 4.2, minus negative 490.5, which is the true weight. This gives us a normal force of 701 newtons. As the elevator starts to move, you'll notice that you feel much heavier than your true weight. So when elevators are going upwards with an upwards acceleration, the normal force is much greater than the force of gravity, and you feel heavier than you normally are. All this comes down to the idea of g-force. Maybe you've heard about a car accelerating and having a certain number of g's. G-force is a measure of the ratio between your true weight, which is just your weight, and your apparent weight, which is the weight you perceive. We can calculate g-force by dividing your normal force by the force of gravity. When you are sitting still, like you are watching this video, your normal force equals your force of gravity. And because of this, the g-force, which is normal force over force of gravity, equals 1. We call this 1g. And you have 1g when you're stationary. When you're accelerating, it changes. In the previous example, when the elevator accelerated downwards with 1.5 meters per second squared, the g-force was the ratio of normal force over force of gravity, And normal force was less than force of gravity. 416 divided by 490.5 gives us 0.848 Gs, less than the stationary G-force. When the elevator accelerated upwards, the person experienced an increased G-force. The upward acceleration of 4.20 meters per second resulted in a G-force, which could be calculated with normal force divided by force of gravity, 701 divided by 490.5. This gave a G-force of 1.43 Gs.